Okay, so for section 15.3, polar coordinates and double integrals. Here's one of the problems, number 19. I wanted to walk you through the steps of kind of what I look for, what do I identify, what do we do as we go through and solve these. So one of the first things I would recommend that you do is identify which one's the surface and which one's the region that you want to do. So here, that's the surface that I'm trying to find the volume under. And then this is the region that I'm integrating over. The reason why it's important to know the difference of those is obviously the surface is the function that's going to get plugged into your integral. The region is how you're going to determine the bounds for your integrand. So first thing I'm going to do, similar to the last sections, is I want to take this region and I want to try to draw a graph for it. I want to know what I'm looking at. So here, this region gives me a circle, radius 5. So what I have, though, is what we talked about in the lecture, the notes, the introduction part, is instead of trying to solve this in terms of x's and y's, because my bound on y is going to have a square root of 5 minus x squared, 25 minus y squared, excuse me, is I can represent this in polar form much easier. So in polar, I can write this as, well, my radius is going to go from 0 to 5. And then that's going to go all the way around the unit circle. So my theta is going to go from 0 to 2 pi. So this is what we call a polar rectangle. I mentioned it a couple times when I did the introduction, the notes kind of explanation video, but I don't think I did a very good job of pointing out and specifically showing what it is. Here, we call it a polar rectangle because my r is bounded by 2 constants, and then my angle theta is bounded by 2 constants. Similar to what we had in rectangular coordinates. When we first started, we looked at x values and y values that were bounded by constants. And when I draw the graph of that, I get it's an actual rectangle in my xy plane. Obviously, this is not a rectangle, so to speak, in the way that we think about it in Euclidean geometry, but I'm bounded by constants. So we do call that a polar rectangle. We go so the double integral over the region, I'm going to convert this to polar. So I'm going to have my angles from 0 to 2 pi. And my radius is going to go from 0 to 5. So now I need to convert my function. So here, so if I want to write this function in terms of r and theta, well, it's just going to be r squared. So I'm going to have r squared. And then I have the Jacobian, the conversion factor we talked about for polar. Jacobian we'll talk about later. dr d theta. So now at this point, if I simplify, I can write this integral from 0 to 2 pi, integral from 0 to 5, that's r cubed dr d theta. When we talked about it first, we said, okay, well, I'll do the inner integral, I'll evaluate it, I'll get some answer, and then I'll do the outer integral, I'll evaluate it and get some answer. When I was making the note pages for 15.2, on a couple of the problems, I solved them by separating the integrals apart. This is a good example I want to talk about for that. So if I notice, my function just has r's in it. So that means that I have this d theta has nothing to do with this. This is, in terms of theta, this is just a constant. So what I can do is I can take them and I can actually separate the two integrals apart. Let me write it over here. So if I rewrite this, this is going to become the integral from 0 to 2 pi d theta times the integral from 0 to 5 of r cubed dr. So now solving this antiderivative is just going to give me theta evaluated between 0 and 2 pi. I'm going to multiply that by this antiderivative is r to the 4th over 4 evaluated from 0 to 5. So this is going to turn into 2 pi times, this is going to be 5 to the 4th over 4. So that's 2 pi times 625 over 4. I can write that as 625 pi over 2. So again, back to the original question, I just erased it. That is the volume under the function, or under that surface, x squared plus y squared, that's above just that circle of radius 5.